Good afternoon. Good afternoon and welcome to the MIT 2016 Open House Distinguished Lecture Series. My name is Obasi Onaha and I'm a junior here at MIT studying in course 6-3. For the non-MIT crowd, that means I'm studying computer science and engineering. It's my pleasure to introduce the next speaker in our series, Professor Nergis Mavalvala. Sorry. She is the Associate Head of the Department of Physics and the Curtis and Kathleen Marble Professor of Astrophysics. She earned a BA in Physics and Astronomy from Wellesley College and a PhD in Physics from MIT. She received the MacArthur Fellowship in 2010. Dr. Mavalvala is the part of the team that announced in early this year the first direct observation of gravitational waves with the Laser Interferometry Gravitational Wave Observatory, or the LIGO detector. This breakthrough ushers in a new era of astrophysics, confirming Einstein's general theory of relativity and paving the way for new discoveries. Please join me in welcoming Professor Nergis Mavalvala to the stage.
Thank you, Basi. Thank you. So hi, everybody. Welcome. Can everybody hear me? OK, good. So I am, in fact, going to take you on a journey today. And the journey is going to be to the warped side of the universe. And I think this is the theme you want to carry with you, that when we look out into the universe, we see this beautiful, quiescent place full of shiny, twinkly stars. But when we zoom in on certain regions of the universe, it's a pretty violent and warped place. Okay? And that's where our journey takes us today. Now, I'm going to talk about this search for gravitational waves that Abasi just told you about. It's a 100-year quest, and so we'll go through that a little bit. And I want to say, right up front, I want to acknowledge all the players. And so these discoveries that I'm going to talk about were made with the LIGO detectors, where LIGO stands for the Laser Interferometer Gravitational Wave Observatory. We'll call it just LIGO. That's a mouthful. And the Virgo collaboration, where Virgo is a sister detector in Europe. And the US part of this effort was funded entirely by the National Science Foundation. So I want to acknowledge our funding agency up front. Every time you think about big science, know that, that funding agencies like the NSF are involved. And then the work that I'm going to present is actually done by a team of 1,000 or so scientists who live under an umbrella organization called the LIGO Scientific Collaboration. So I want to acknowledge all of these players. So my own name is up here. I am from MIT, but I'm really just the messenger for this very cool science that our team has pulled off. Okay? All right, so unless you were hiding under a rock, you might have noticed that on the front pages of virtually every major newspaper in any language you can think of on February 12th was a headline about scientists discovering gravitational waves, scientists proving that Einstein was right. I mean, there were many versions of the same story, but it was everywhere. And my talk today is aimed at unpacking the science behind that story for you. Okay? And it's a story of amazing science and also a human story. Okay, so before I tell you much about gravitational waves, I want to bring us back to a tool that's very familiar to us, which is light. And one of the very spectacular things that we see when we look out into the universe are objects like this. This is Cassiopeia A. It's a supernova remnant. What happened here? Well, about 300 years ago, there was a star just like our own sun, more or less. But it had run out of nuclear fuel. This will happen to our sun eventually, not for a few billion years, so be calm. It'll run out of nuclear fuel, and when it does that, it stops shining. And when it stops shining, its gravity becomes so huge that it kind of crashes in on itself, it implodes, and all this material falling in causes a shock wave that then causes an explosion. And that's what happened. The star went supernova. And this is what we're left to see at the end of this. So we are now observing this object several hundred years after the star actually died. And it's one of the most beautiful, one of my most favorite pictures in astronomy, because it also has a few other interesting elements to it. Notice all the different colors. So this picture was actually taken with 3 different types of telescopes. The green and yellow parts are familiar wavelengths of light, optical wavelengths that our own eyes can see, and that was taken with the Hubble Space Telescope. The red parts were actually taken with an infrared telescope, also a space telescope called the Spitzer telescope. And then the blue and purple parts were actually photographed using the Chandra X-ray Observatory. Now, why is that so important? That's really important because these different colors of light tell us about different energies involved in the process. And you notice that, for example, X-rays are the most energetic radiation. And you see that the outer edges of the supernova remnant carry all the X-rays. Those are the most energetic parts of the explosion that got out the farthest. Okay? Now, there's another very important and beautiful piece in this picture, which is this little blue dot right at the center there. Now, this little blue dot appears only in blue. If you looked at it with just the infrared, you wouldn't see it. It doesn't shine in infrared. If you looked at it with optical, you wouldn't see it. But in X-rays, it's there. What is it? It's an object called a neutron star. And it's actually the remnant of the parent star that died. This neutron star is an amazing creature. So it has the mass of about our sun, but in a radius that's 10 kilometers. So it's it's about the size of Cambridge, but with the mass of our sun. Now remember, our own sun has a radius of about 700,000 kilometers. So it's much, much smaller, much more dense. And that means the gravity around this star is much more ferocious, if you will. And we'll talk about ferocious gravity in a bit. Now, if this parent star had been a little bit heavier, if it had been 3, 5, 10 times the mass of our sun, instead of the new object in the center being a neutron star, it would have been a black hole. Okay, and that difference between the neutron star and the black hole in terms of how they're born is just that. Lighter stars, when they die, give birth to neutron stars. Heavier stars, when they die, give birth to black holes. Now, how might we see a black hole? Well, it turns out that we do actually observe evidence for black holes usually using, again, X-rays. So this picture here, by the way, have no illusions. This is actually just an artist's rendition of what a black hole would look like. We do not observe them in such clarity and beauty. But what's going on here, and the reason maybe in case people haven't sort of caught on, black holes are objects that have so much mass packed into such a small volume that the gravity is so strong that even light cannot escape. Hence the name black hole. Now we see black holes by observing gas and dust around the black hole that's swirling around the black hole as the black hole spins. And that's what this picture shows. This is actually a reconstruction of what we think the data, again from Chandra X-ray Observatory, showed us, where there is gas and dust around the black hole that's actually flickering in X-rays because the gravity of the black hole is so strong that it's swirling all this gas and dust and heating it up. And when it heats up, it shines in X-rays, okay? But really, we've never directly observed a black hole. We've never been able to go out and say, there in the sky is a black hole, and here's what it looks like. Why not? Because the tool we've had so far as astronomers is light. And this has been has been true as long as human history. People have looked out in the sky and looked at stars with their eyes, and then we got a little bit better as we made telescopes, but it's been light. So how might we find black holes or other dark objects in the sky that do not give off light? Gravity. Gravity is the one thing that black holes have a lot of. So is there something we can do with gravity? Now, to answer that question, first we must try to understand what exactly gravity is. And I'll start with the first hero of gravity, that was Newton. And Newton in the 17th century had this extremely successful theory of gravity. It was actually also quite simple. We teach it to kids in 7th, 8th, 10th grade, of Newton's laws. Now, what it said was quite simple. If you have a mass, m1, and another mass, m2, and they're separated by some distance, r, they feel a force. Each one feels a force that's proportional to each mass and inversely proportional to the square of their distance. Beautiful, simple, and mostly it worked. Newton worried about something, and actually the ancients before Newton, even as far back as Aristotle, worried about questions like this. It was a question of something called the action at a distance. And what does that mean? That simply was the question of how does this mass here know about this mass there? They feel the force, but how do they know about each other? What carries the information about this force? And that actually did not get solved for a few centuries until our next great hero of gravity showed up, and that was Einstein. Now, Einstein was quite radical in many ways, and I'll keep coming back to this, but one of the things that he said to us was gravity is not a force. All students in the room sit up. Gravity is not a force. Einstein told us that gravity is the warpage of space-time. Now, this is a pretty radical idea. When we think about empty space, we just think, okay, space is empty. Light travels through that space. Nothing else happens. Einstein told us, no, that space can curve, it can warp, it can ripple, it can wiggle, it can even tear. Okay? So it's all these things that space-time can do. And how do we understand it? The way to understand it is these kinds of pictures that we've now famously seen, where if all of space-time is a grid and you put a massive object like a star in the middle, the grid deforms or curves. Now, a simpler analogy, not a very complete one, but a simpler analogy is to just think of our own everyday experience. Imagine you took a nice cushion, nice and flat, firm, stretched, and you put a bowling ball in the center. What happens? It curves. Now, imagine you took a little playing marble and you put it at the edge of the cushion. What's going to happen to the playing marble? It's going to fall into the bowling ball. It has no choice but to fall into the bowling ball because of the curvature of the cushion. And that was Einstein's picture, which was just that if you have a little planet that's sitting next to a star or a moon sitting next to a planet, it has no choice but to follow the orbit that it does because the star deformed the space-time and made the curvature. And so that was the picture that he then carried, and it was famously rewritten in this poetic form, which says, matter tells space how to curve. So the bowling ball told the cushion how to curve. And then the curvature tells matter how to move. The curvature of the cushion forced the playing marble to fall into the bowling ball. So that is now the picture you must carry for gravity. No longer a force. Anytime you see a massive object, just know that around it, it has warped its space-time, including us. We're doing this too. It's just immeasurably small amount of warpage. Okay? All right, now, what happens then if you took that bowling ball and instead of just letting it sit flat on this cushion, you bounced it up and down? This was a question Einstein asked. And to his horror, it turns out that just as you would expect in your own imagination, there'll be ripples on the surface of the cushion. The cushion now no longer is just curved, it curves in a ripply way. Okay? And that was what he found both conceptually, but also from his equations, which are encapsulated in this incredibly, this is one of such a benign looking equation, just 3 or 4 terms and so simple. It is one of the most horrible equations to solve in physics. And in fact, even today, 100 years after Einstein first wrote down his field equations, we only have a handful, like 3 examples of exact solutions. Okay, so even though it looks very sweet, it's actually rather horrible. But came out of this equation were this idea that the space-time can ripple, just like the surface of the cushion. And in fact, it would look like this. Here is a star, and as the star bounces up and down, you can just see that the grid that represents space-time ripples, and these ripples travel outwards. Okay? And if you don't care for this and the analogy of the cushion, you can carry another analogy with you, is if you drop a rock in the middle of a still pond and the ripples spread outwards. And that's sort of what space-time does as stars bounce around, and stars do bounce around. So this is something we do have to consider. Okay, now when you think about doing astrophysics, one of the things that you really like to think about is, well, we've done astrophysics for centuries with light. Can we use these gravitational waves profitably? Okay, and the answer is yes. Now, how do you make light? Well, we teach students in high school, and it's sort of true. If you want to make light, you take charge and you accelerate it. So you could, if you had a sensitive enough system, just pull an electron out of your pocket, bounce it up and down, and light should radiate. Okay? Same thing is true for gravitational waves. Instead of charge, you need to accelerate mass. Now, it turns out that with light, you can make these very pretty pictures. You can make images. And the reason is that the wavelength of the light is much, much shorter than the size of the objects that we're trying to image. Now, it turns out with gravitational waves, you cannot make images, but you can make waveforms. Now, what does a waveform mean? You're going to see many, many waveforms, so I hope you get excited about them right now. So a waveform is simply something where you see a change in the space-time as a function of time. You can literally think of this waveform as the bumps and the peaks and troughs of the space-time itself as a gravitational wave goes by. Okay? Now, there's one property that is very important for astronomy. It turns out that light is actually very friendly. Light, every time it meets matter, it gets absorbed, it scatters, it disperses. Gravitational waves, on the other hand, are extremely aloof. When they hardly interact with matter at all. They meet some blob of matter, they go right through it. Now, an easy way to sort of get a handle on that is imagine you went to a party. And you went to the party with an extrovert. Okay, what happens? It's time to leave. Honey, I'm ready to go. Can we go? So by the time you actually get out of the party, it's taken an hour, because the extrovert actually meets people, gets stuck, chats for a while, then go a little bit further, meets again, chats. It takes a long time to leave the party. And that's light. Gravitational waves, on the other hand, extremely aloof. They don't really interact with people. The best that you might expect is they'll find the host, say goodbye, and you leave. They get out right away. And this is a property that will come very handy as we try to understand the universe using this tool. Now, one other thing that's interesting about these light versus gravitational waves is light is due to very fast oscillations of charges. Electrons really can oscillate very fast. They're very light. Whereas, on the other hand, when you take large, massive objects like stars and you try to oscillate them or bounce them around, they don't go very fast. And so the frequencies associated with gravitational waves are very low. They're usually at the kilohertz or slower, which is typically, you can think of them as objects that sort of go at speeds of blenders or a little bit slow, or much slower than that. Okay? All right. So what kinds of objects would give off gravitational waves? What are the ingredients? We need two things to make a gravitational wave. First of all, you need a lot of mass, and that typically means you need compact objects like neutron stars or black holes, things that have a lot of mass in a small volume. And then you need rapid acceleration. If they're just sitting around, they don't radiate. So acceleration means you need orbits. They have to be orbiting each other, or they're exploding or colliding. So this should immediately now bring you back to the starting point of my lecture, which was the violent and warped universe. What we're looking for are objects that have the masses of stars whipping around in orbits or exploding or colliding. So you get a lot of space-time warpage, and these are pretty violent places, thankfully far from where we are. Okay, so what kinds of things could that be? Colliding compact stars. So every time neutron stars or black holes merge or collide with each other, there should be the storm of gravitational waves coming out of them. Supernovae. It's a phenomenon that I've just shown you, where a star dies and it explodes, and that should give off copious amounts of gravitational waves. Now, there's another source that is actually one of the most profound and also one of the hardest, and something that we don't have a good shot of measuring in the next, in the next generation or so, which is the Big Bang itself. Now, it turns out that if you want to know what happened in the very early universe, what do we know about it so far? We know about it from light. And the very first light from the early universe we call the cosmic microwave background. It's just a shell of light surrounding the whole universe as we can observe it. But the most important thing about it is that that light came to us, the shell of light we see, was formed when the universe was 400,000 years old. Why? Well, at moments earlier than that, when the universe was younger, it was too hot and too dense, and our friendly photons were chatting with the hot soup of matter. They never escaped. And so only when the universe had expanded and cooled off enough, which was at 400,000 years of age, did the photons escape that early soup and start streaming towards us. Okay? So if we want to know about the universe at earlier times than 400,000 years, which many of us would love to know, what can you do? Well, you can't use light. You can use gravitational waves. Gravitational waves were in the early universe just as light was, but they were not interacting with the matter. So they have been streaming towards us from the very earliest moments after the Big Bang. So if you could pick up this background sphere of gravitational radiation, you could look farther back in time at the earliest part of the universe. And this graphic just shows us, as we look back in time, the cosmic microwave background kind of cuts off at 400,000 years. This is just a big glow of light because we really don't know what happened in that time there. And then if we could go back to the gravitational waves, we could see, farther back in time. And then, of course, I've only listed the things for you that I can think of, but we can also imagine that the universe has secrets that we don't yet know how to ask about. And those are the kinds of things that we can look for with gravitational waves. Now, here then is a movie. And this movie is actually the story of two black holes. Here are the two black holes. And these black holes happen to be sitting in this star field. So these are individual stars. There's some gas and dust around, and all of that glows with light. And what happens to these black holes is that they're orbiting each other. And as they orbit each other, they lose energy to gravitational waves. And where does that energy come from? That energy comes from their orbit, which means they must get closer to each other. So the story of black holes or neutron stars that are orbiting each other, where gravity and warpage of space-time is so large, is that they must lose energy to gravitational waves. This is quite different than our moon and the Earth system. Gravity there is not strong enough, otherwise the moon would have crashed into the Earth too. But that will take longer than the age of the universe just because the space-time curvature isn't strong enough. And so this is then what happens. The black holes orbit each other. As they do, the sheer gravity deforms the light that's around them. You can see this deformation here. And indeed, as they get closer to each other, the black holes will spin faster and faster, and eventually they'll collide and become a single black hole. Now, one of the things that you might find interesting are these little backgrounds of light here. And some of you who have seen Interstellar, the movie, might recognize that. What those edges of light was light from behind the black hole that was getting bent around and appearing to us in front of the black hole. And that is the power of gravity in Einstein's formulation. Einstein was also the person who reminded us and actually formulated for us that in strong regions of gravity, light itself does not follow a straight line. It bends. Okay? So students sit up. We teach you in school, light follows straight paths unless it bumps against a mirror or something or refracts. It's not true. If you put light around a big enough gravitational object, it will bend. Okay, so Einstein, it turns out, was very ambivalent about this all. He proposed gravitational waves in 1916 as part of his original formulation of general relativity. And right there, he showed that gravitational waves must exist, but he remained extremely unsure about it. And in 1918, he actually gave a correct formulation. Turns out the 1916 formulation wasn't quite right. There's another thing students should notice. The great man himself made mistakes. Okay? But he remained really unsure about this. And not only was he unsure that because he had calculated that the effect is really, really, really weak, but he also wasn't really sure you needed this wiggling, time-dependent part of the theory. And in fact, in 1937, he submitted a retraction, and then he retracted the retraction that same year. Okay, so you can tell he had this ambivalent relationship with gravitational waves. The doubts and controversy actually subsided not until 1957, and I will say this actually with great conviction, and as an experimentalist, as someone who builds instruments and observes. The experiment and observation always have the final say. The great man made a theory, but again, nothing could prove that theory right until we could say nature behaves this way. And that first evidence for Einstein's gravitational waves came in 1974. So in 1974, two scientists, Hulse and Taylor, discovered a binary neutron star system. What does that mean? Two neutron stars in orbit around each other. Very much like the movie of the black holes that I showed you, which means as they're orbiting each other, they should be losing energy to gravitational waves. If they're losing energy to gravitational waves, they should be getting closer to each other in the orbit. And that's what this data shows. On the horizontal axis here is just the year, so 1974 when they discovered it. And then this data goes out to 2005, but since then they've added more points as well. And on the vertical axis, this is this big mouthful. It simply is the size of the orbit. It simply shows that as time went by, the orbit was getting smaller and smaller. That's all that it shows. But the most important thing about this measurement was that they were then able to compare the rate at which this orbit was growing smaller to the prediction from Einstein's theory. And that's what this solid line is. It's not a fit to the data. It's not just the curve that fits the data really well. It is the exact prediction that the formulae that Einstein wrote down in 1918 would give for this system losing energy to gravitational waves. So this was considered the first indirect evidence that gravitational waves are out there and that they do get radiated. And it also impressed Sweden. And they won the Nobel Prize in 1993 for this measurement. So that put to rest one big issue which Einstein never lived to see. He was actually, even by the discovery of the binary neutron star system, he was no longer with us. But that gravitational waves are out there and they behave like his field equations would predict. So let me just say his ambivalence was justified because the first evidence for these neutron stars and black holes did not come in his lifetime. Even so, one of the most remarkable things about Einstein and his theory was that formulated 100 years ago, it still made firm predictions about gravity, space-time, and black holes. How should they behave? So now here is a movie. And this now is a simulation of one of the few exact solutions we have to Einstein's equations. And this came about with supercomputers. Starting about 10 years ago, scientists were able to crack the codes on how to get these systems to, how to solve those equations. So this is a pair of black holes. And what I want you to follow is this curve here. You'll see as these black holes get closer to each other and then finally collide, general relativity tells us exactly what the waveform should look like. Okay, so here are the black holes. And what you'll see is the black holes are, as they orbit each other, these little arrows that you see are simply are arrows that mark the space-time curvature. And you'll see these arrows get bigger and bigger, and the space-time gets more and more warped as the holes get closer to each other. And here is the waveform. It looks kind of just like a simple old sine wave, as any orbiting system should, except when they get very close to each other. And then you will see some spectacular sort of warpages of space-time, a real storm. And the movie will slow down at that moment so we can see what happens. You can see the arrows are getting bigger and bigger as these holes are getting closer. And now the movie slows down. These black holes are about to touch each other. Their horizons are about to meet. And you can see how warped the space-time gets then. And right there, they've touched each other. And that's where the waveform kind of, and now they just merge very quickly into a single black hole. And then the single black hole has no orbit, and so there's no acceleration, and so the gravitational waves turn off. And then these waves take off into the universe, waiting to be detected by a species like ours. Okay? So that's the process by which gravitational waves form, and the waveform that Einstein predicted was the one that I show you here. Now, it turns out that general relativity also allows us not just to predict the shape of the waveform, but it also allows us to calculate how strong these waves should be. And the strength of the waves for gravitational waves are given by a quantity h, which is called strain, and I'll tell you in a moment why, as a function of time. And in the 60s and 70s, Professor Kip Thorne, who is now a professor emeritus at Caltech, some of you know him from Interstellar, this was his day job. He was actually calculating these waveforms from systems like neutron stars and black holes. And people were able to show, in his work and others, that the size of the wave was 10 to the minus 21. So it's a very, very small number. So this is what you expect the strength of this gravitational wave to be from a pair of neutron stars that are in a galaxy near our own. Okay? So it's a pretty small number, and people should be stunned. But you might not be so stunned because it's actually a dimensionless number. I haven't told you really yet what it is, but you can already start to imagine what it is. It is something that measures the warpage of space-time, the size of the ripple of space-time itself as the wave goes by. Now, it turns out that because these gravitational waves from neutron stars and black holes are due to objects that are spinning at hundreds of hertz to kilohertz, this turns out to be right in our human audio band. As a result, one of the things that we like to do is to encode these signals into sounds, and our colleague here at MIT, Professor Scott Hughes, encoded this one. And so this is simply taking a signal like this and encoding it into a sound. And what you'll see is a very characteristic chirp. I have lost my mouse, but here it is. So this is that same waveform, low frequencies, and it's getting to higher and higher frequencies and higher amplitude. Okay, that's it. So what was that last whoop? That was the two neutron stars at the moment they collided. Okay, so what's happening is they're getting faster and faster around each other, and boom, they collide. Okay, so that's what what it would sound like, and this is part of why scientists are fond of saying gravitational waves are like listening to the sounds of the universe. Okay, it's because we do encode them into sound, even in our detectors. All right, so let me just give you a quick summary of what we think gravitational waves are. They're predicted by Einstein, as we said. They're ripples of space-time itself, but they have one very important property, very important if we want to detect them. And that is that they stretch and compress the space-time itself. What does that mean? It means that as a gravitational wave goes through me, I'm a space-time object. I'm attached to space-time just like we are. As it passes through me, it actually stretches and compresses me at the frequency of the wave. So I get a little bit shorter and fatter, and the next half cycle I get a little bit taller and thinner, and that continues to happen. And you can see right away why this is going to be important, because what we're going to do when we build detectors is to come up with a way of measuring those changes in space-time. Okay, the changes in space-time between two masses that are free to move is an amount delta L, which is proportional to distance between the masses. Now, what does this mean? Let me just say, this simply means that if I take some ring of objects and they have some distance L between them, when the gravitational wave comes by, it deforms that ring by an amount delta L. And now the big question is, how big is that effect? And that's where we get really sobered. The amount by which, if I have some distance L, I am an object of about 1 meter in distance. If this gravitational wave with amplitude 10 to the minus 21 comes through me, it changes my size by 10 to the minus 21 meters. Now that's a small number, because I've put a scale on it. Let me ask you, does anyone know what's the size of a proton? 10 to the minus 15 meters. So this is 1,000,000 times smaller than a single proton. Okay, that's the effect on me. So clearly, I would not be a very good gravitational wave detector. What are we going to do? Well, there are a number of ideas. But let me start by simply just telling you a little bit about the concept of how we do it, and then we'll get to how it's really done. The concept is very, very simple. You take a laser beam, and you shine it at a mirror that's some distance L away. Okay? The light reflects off the mirror and comes back to you, and if you have a really good clock, all you do is measure how long did it take for the light to hit the mirror and come back to you. Measurement done. When the gravitational wave comes by, that distance will change, and your clock will give you a different time. Right? Now, it turns out that even for large distances, we don't have clocks that are good enough to do that. That simply doesn't work because the precision of clocks is not available by many orders of magnitude. So instead, what we do is we build an experiment like this one. We take the same laser beam, and we split it into two halves on this beam splitter. Half the light goes this way. The other half of the light goes through. Each of these beams reflects off two mirrors, comes back to the beam splitter, and it interferes there. So this is called an interferometer. Some of you will recognize this as the basis of the Michelson-Morley experiment that was done when we were looking for the luminiferous ether. Now, it turns out, why is this better than this? And there's one simple reason. which is that in this case, on the case of the interferometer, we don't need an absolute clock. All we're doing is we're comparing the light travel time along one arm to the other arm. And because it's a comparison, you can think of it as one of these arms acting as the reference. You don't need a very good clock anymore. You just need a very still and stable arm. So now you have two things you have to do to make this gravitational wave detector. You have to do them really, really well, but it's just two things. The first thing is you have to make mirrors that are very, very still. Remember, the motion that we're trying to detect is, tiny fractions of the size of a single proton. Now, everything on the Earth wants to move our mirrors by more than that, so we have to do a lot of good vibration isolation and also protect the mirrors from thermal jitter. Now, if you've done that, imagine you've made a mirror that's really, really still. Is that any use if you can't measure very small motions? And that's where our laser light comes in. Our laser light is actually the meter stick by which we can measure such tiny motions. And that's what we do. We use precision interferometry to actually measure the positions of these mirrors. But those are the two things you do. You put those together, and you get a realistic experiment. So this is Ray Weiss. He was a professor. He is a professor here at MIT, emeritus now. He came up with this idea of using an interferometer to detect gravitational waves. And for some of you, this will be amusing. He came up with the idea when he was teaching a course here on general relativity at MIT. And he actually was someone who worked with lasers. So now keep in mind, so this was in the late 60s and early 70s. The laser had just been invented in 1960. So what does Weiss do? He says, well, I know and I like lasers, so we could think about using lasers. Then he says, well, that's not going to be good enough. He says, let's make it long. And then he comes up with the idea that we should make it 4 kilometers long, 4,000 meters, which is the longest that you can make a path on the Earth where a laser beam can still go in a straight line before the curvature of the Earth makes you have to dig. Okay, so that was the longest you could make it. And then, lo and behold, the measurement we have to make is only 10 to the minus 18 meters. That's just 1,000th the size of a proton. Piece of cake, right? And in fact, that's what he thought. He said, that's not so bad. We can try it. So he invented the idea of using this kind of interferometer, using a laser interferometer, making it kilometers long. At the same, in 1972 was when he wrote the full proposal for it. At the same time, Skip Thorne at Caltech was thinking about the theory. And the two of them came together and decided that it might not be so crazy. Let's just build one of these. And that was the birth of a very bold experiment. That was LIGO, the Laser Interferometer Gravitational Wave Observatory, which has 2 detectors, one in Louisiana and one in Washington. They're 2 L-shaped detectors for reasons you now know, because one arm acts as the reference for the other. And they had to be designed to be capable of measuring changes in distance of 10 to the minus 18 meters over 4 kilometers. So just keep in mind what this means. So this means is that they have to be able to, laser beams travel for 4 kilometers, and as they travel over 4 kilometers, we have to be able to tell that they travel 4 kilometers plus or minus 10 to the minus 18 meters. Okay? Now you put it all together, and here's a quick tour of the observatory. So this is our Louisiana observatory, L-shaped as promised. This is the beam tube in which the laser beams run for for 4 kilometers. They're covered by concrete housing like this, which has its utilities. So this is not Photoshop. This is true. This is now in our Washington observatory, where this patrol car came over this dune and simply didn't notice that there was this 4-kilometer barrier in the middle of the desert. These are vacuum chambers that house a mirror. Each one of these houses one mirror of the interferometer. They're quite big. If I stand next to these, the top of my head would be just below this row of viewports. Why so big for a single mirror? I mean, most of us are used to seeing mirrors in our labs, and when you've been to labs today, you'll see they're kind of this big. Well, the LIGO mirrors are not just kind of this big. They're this big. They are 40-kilogram pieces of glass, 35 centimeters in diameter, and they're hanging off of many, many layers of vibration isolation systems. So vibration isolation systems that look like this, springs and masses. This is very much like the shock absorbers in the suspensions of your car that are removing vibrations. The mirrors themselves look something like this. So, and they each are also hanging from multiple layers of pendulums. It turns out pendulums are good filters for vibrations at the top there. And so this is part of the vibration isolation system. And then finally, there's a laser, and this laser can put out 200 watts of laser power. Does anybody know what a laser pointer typically puts out? One of these, I won't shine it at your eyes, but milliwatts at green. This one happens to be infrared, and it's 200 watts. You do not want to, get into contact with that laser beam. It would cause you severe tissue damage. Okay? All right. The control room looks like this. This is where the experiments are controlled, and all these different graphs are just ways in which we measure the health of the instrument. And when you put it all together, you get curves like this one. Now, on this axis here, you have frequency. And notice one thing very fun about the frequency. It goes 10 hertz to 10 kilohertz, human audio band. The gravitational waves we're trying to detect happen to be in the human audio band. On the vertical axis is simply just a funny measure of the strain. And so again, here's the 10 to the minus 21 number that we were targeting. And these curves are, the red curve was the first phase of LIGO that was built between 2000 and 2010. And the red curve was the design sensitivity for that. If a gravitational wave came by, it would have to be in this region up here. It would have to be so strong for us to see it. If it's below these curves, it's too weak for us to see. Now, it turned out that we ran these instruments for about 10 years, and we didn't see any gravitational waves. So we set about designing a more sensitive instrument, which is this curve here. This is called the advanced LIGO curve. And the improvements that were necessary, I actually won't go into the improvements that were necessary to do this. I'll simply just put them up here, that we had better seismic isolation, we used better materials, we used more laser power. I'll leave it at that. I do want to say one fun thing about the red curve. Remember Ray Weiss? So this is the curve that he wrote down in 1972 and observed that we achieved it in 2010. So this has been a long journey from the time that he had the idea to the time that it actually was built and working at the first level of sensitivity. Now, why do we make these curves go lower and lower? It's the same as when telescopes improve. Some of you will recognize this object. This is Saturn. If you had a better telescope, Saturn might look like this. If you had a really good telescope that flew right by Saturn, it would look like this. And that's just the same game we're playing when we pull our curves down. We're just trying to make better and better telescopes to look at fainter or more distant objects. All right, this is part of a global network of detectors. Here are the two LIGO detectors that are in the US, in Washington State and Louisiana. Those are 4 kilometers long. In Europe, we also have in Italy a 3-kilometer long detector, which was not operational at the moment. It's going to be up probably end of this year. There's also a 600-meter long detector in Germany. It's a short little guy. And then there's a detector being built in Japan called Kagra, and a planned detector in India. And then very much out into the future, scientists have also thought about a space detector called LISA, which is the Laser Interferometer Space Antenna, where LISA would have arm lengths of 5 million kilometers. So you can see delta L gets very big then, because for the same age. And so that's a big advantage, but that's far in the future. Now, let me talk about the event that caused all the stir in February. Yeah. So on September 14, 2015, the LIGO detectors detected a binary black hole collision. This is the operational state of the detector, which was the red curves here. Now, you already saw the green curve, which is the previous version of LIGO. And the red curve is quite a bit lower, which means we had a better detector operating for advanced LIGO. And so here is the journey of the gravitational wave. So here are the two black holes. And you can see the two black holes will collide with each other. These gravitational waves are emitted. They go across the universe as they're propagating towards us. And eventually, 1.3 billion years later, they arrive. So you can see the movie's a bit sped up. They arrive at the Earth. And the other thing that isn't very realistic about this movie is that the scale of the effect is very exaggerated. As these waves come through, the Earth doesn't quite wiggle this much. It certainly wiggles, but not quite so dramatically. And what we saw was a signal that arrived first at our Louisiana observatory, which is the blue data. And then 7 milliseconds later, so this is shifted on this curve, the same signal arrived in our Washington observatory. So it came from the south, going north, through the Earth, and it registered a strain of about 10 to the minus 21 at the peak, which corresponds to a displacement of 4 atometers, or 4 times 10 to the minus 18 meters. So this was the data. You've all heard me say, and you've heard maybe elsewhere too, that we like to encode these into sounds. This is what it sounded like. Oh, I guess I have to play the sound from here. Thump. Okay, now this is sped up by a factor of 2, so it's more pleasant to our ears. So this is the original. All you hear is a thump. Okay? And in fact, this is the chirp in time frequency space. You can see as time goes by, frequency goes up for both of these. So that was what the signal sounded like, and we like to think of this as the chirp that was heard across the universe. Now, this is what the waveform itself looked like. This was the waveform we could reconstruct from the data. And from this waveform, because the frequency is changing with time, we could tell what the masses of the two original black holes were as they were orbiting each other. From the way that the amplitude of the wave was changing with time, we could tell how far the black holes were. And finally, in this part of the signal, by watching this signal change in frequency and time, we could tell what the spin and mass of the final black holes were. And what did we learn? We learned that once upon a time, 1.3 billion years ago, there existed 2 black holes. They were big black holes. They were about 30 times the mass of our sun, which was a surprise. Astronomers did not know black holes could come in that size. They danced in orbit about each other, and they emitted gravitational waves, as Einstein had instructed them to do. This made them get ever closer to each other and orbit ever faster. They were moving at half the speed of light just before they collided. Imagine that, an object 30 times the mass of our sun whipping around at half the speed of light. You can see that space-time was enormously warped there. And in fact, as they merged to form a bigger black hole in the midst of a spectacular storm in space-time. The newly formed black hole, we learned, was not as massive as its parents. In fact, 3 solar masses were missing. Where did they go? They were converted into gravitational wave energy. And what that means is that for that brief instant in time, for a few hundred milliseconds as these black holes collided, there was more energy released than all the shining stars in the universe emit. Okay, so it's an extremely powerful explosion. Some will claim the most powerful explosion since the Big Bang that we have observed. Now, what else did we learn? They did not live happily ever after, right? The black holes died. But let me say something very neat about that. These 2 black holes died, but remember, a new black hole was born. Okay? So there is life after death. Now, here is how well we could tell where the black holes were localized, which is this big banana-shaped region of the sky. So it turns out gravitational wave detectors have a good analogy to our ears in another way. When you look out with your eyes, you can see exactly a single point. I can be staring quite exactly at that mic, and I can see it. But our ears are not so directionally sensitive. We can tell that, okay, the sound came from here versus there, but I can't tell you exactly where the sound came from. Gravitational wave detectors are the same way. We can't really tell where these signals come from. So let me just finish by telling you what lies ahead. LIGO will start its second observing run in the fall this year, and we hope to actually have an improvement in sensitivity that will allow us to see maybe up to 5 binary black hole events. And we're marching towards our final design sensitivity over the next 3 or 4 years as our partner observatories, Virgo, and the Japanese detectors and the Indian detectors come online. I'm going to end with just telling you why this is so exciting. So why did the newspapers carry those headlines? So this is the first direct observation of gravitational waves, the first direct measurement of this time-varying space-time that Einstein talked about. It was the first direct observation of a black hole binary system. We have never seen black holes in real time colliding the way they did. It was the first test of Einstein's theory of general relativity in this strong field limit. We've all seen general relativity be very successful, but we've never really measured it around a black hole system like this. Why is that important? Now, if you remember Newton, one of the big sort of gaps in Newton's theory was it worked beautifully for our solar system, except for Mercury. What's special about Mercury? It's closest to the sun. That means it had the strongest gravitational field in the solar system, and even for Mercury, Newton's theory didn't work, and we needed general relativity to explain the orbit of Mercury. So maybe around black holes, even Einstein isn't right. What we found was that so far, for this one system we've seen, he was pretty right. Okay, and as someone who spent my whole career designing the LIGO detectors, was also a great deal of relief that the machine actually works at these atometer scale precisions. So that was a very nice thing. Most importantly, if you take away nothing else from my talk, take away that what we've done is we've really turned on a completely new sense with which to study the universe. No longer do we rely only on light. We can also now rely on a second messenger, which is gravity. And surely there will be things we have not imagined. So 400 years after Galileo in 1609 started with the first telescope. It was a small little 1.5-inch mirror diameter telescope. And he was able to tell that the moon had craters and mountains and so on. But he studied the phases of Venus, but that was it. It took us almost, 300 years later, from 1.5 inches, we had learned to build 100-inch telescopes. Then another almost 100 years later, we knew how to put a 100-inch telescope into space. And now we're on our way to building 25-meter diameter telescopes. So this is the trajectory from Galileo's sort of at the time, from now, looking back in time, from where we sit, rather modest telescope. We also learned to add many other colors of light to our observations. Now, it turns out gravitational waves are the same way. They have many, many colors. The ones that we're looking at are wavelengths, are periods of frequencies of 100 hertz or so. But there are also objects that are radiating these at much, much lower frequencies with periods that are even as long as the age of the universe. And all these different kinds of technologies are going to be deployed to study them. So I do believe that the next century is going to be a century where gravitational waves are going to become an important tool for the observation of the universe. Thank you. Questions? Sure. Would you come to the mic, please? I'm told that we should use the mic, or I'll repeat the question, either way.
So with more detectors on the planet, can you actually localize better where the black holes were originally?
I'm sorry, when you...
With more detectors?
Yes, so the question was, if you had more detectors, could you actually localize better where the black holes were? And the answer is yes. And in fact, this is what the answer would look like. This is how well you can localize sources on the sky. And you see here are these banana-shaped regions. If you had just the detectors in the US and in Europe, okay? So that's the two LIGO detectors and the Virgo detector. Now imagine that in a few years, the Indian detector came online. The same region of sky would suddenly look like that. So the bananas became little dots there. And as you add more and more detectors, you can get more and more precisely where the sources are located. So yes, that's part of the reason for this global network of detectors is motivated by being able to pinpoint. Now, why do we want to know where they are better than what we can do? Because one of the ultimate dreams, and I think astronomically very useful things, is if we could then tell partner telescopes and telescopes using light, we saw an object, point your telescope there and see if you see something with light. And if we tell them that it's a region of sky that's this big banana here, they'll laugh at us because telescopes it would take them days to map out such a big region of sky. So if we can pinpoint more carefully, telescopes could then go point at those regions. And one of the ways that you can think about why that's so useful, an analogy that I have found very, very useful in thinking about it, is like, going to the movies. And if you can go to a movie, and if you were silent movies before you had sound, there was a lot of information missing. And then you added sound. It's the same as when you have a light telescope and you have a gravitational wave telescope looking at the same object. You can put them together and reconstruct everything that's going on inside of the object. So that's the reason for having so many. Other questions? Sure. Why don't you come down to the mic, or yeah, come on down to the mic. I'll take you next. Go ahead.
Some decades ago, wasn't there a researcher, Weber, who made some claims of detection? Does the LIGO claims debunk or prove that he was right?
Yeah, so the question is, wasn't there a researcher named Weber who made claims of detecting gravitational waves? So yes, so Weber was in the 1960s, and he actually used a different technology, not interferometers, and he made some very emphatic claims that he never really backed away from, that he had detected gravitational waves with a strain of 10 to the minus 15. Okay, so not 10 to the minus 21, so a million times bigger. And in fact, many people, first of all, astronomers really struggled with that because people could not come up with systems that should radiate such strong things unless they were in our solar neighborhood, and then we'd feel them in many other ways. And then the other thing was, many people then, after Weber, built instruments like his and could never reproduce what he said. So largely it was debunked long before LIGO. But it's even more confirmed that they are in this scale of 10 to the minus 21. They are not 10 to the minus 15 unless it's really, like I said, very nearby, and then we would have much other effects from it. You had a question. So there's two questions here. One was that, I'll take the second one first just because I remember it. So the idea is that if these gravitational waves are traveling outward, how come they come out in waves and not just a single burst of energy? And the answer is that they are actually just a single burst of energy. It's a one-shot. That wave, you can think of it as a wave package. You can think of it just as, imagine the following. I drop a rock in a pond, and I'm a boat sitting a little bit far away. And the ripples go by, and when they go by the boat, they bob me up and down. That's the same as what the gravitational wave did. It bobbed our mirror in our detector, and then it traveled on its way. And so it is actually, it is just a single wave going by from that one rock being dropped in the pond. Okay, so that's the first. The first part of your question was, I'm sorry, I've already forgotten. Yes, okay, good. Yeah, so the second question was, waves have to travel through a medium, and so what's the medium here? Now, this is one of the things that was very hard about Einstein's theory. So even electromagnetic waves, light waves, they don't really need a medium per se. Vacuum is the medium. Now here, what is the medium? The medium is the space-time itself. And that was the thing that was very hard to wrap your head around, which is that space-time is doing the distorting. If you put your mirror out there, if you put some object out there and you had some precise way of measuring its motion, as we did, you will see it move. And so it's the space-time itself that's doing it. It can be vacuum. Look, these waves went right through the Earth and came out the other side. So the medium is the space-time itself. If you want a visual of that, the best thing I can suggest is to just think of the grids that you see, the grids that we show you. It's the grid itself that's doing the wiggling. That's, but really what it is it's the space-time itself. So, go ahead.
I have one question for, can you predict when can you observe the GW next time?
Yeah, so the question is, can we predict when will we observe the next gravitational wave event? So the answer is, in a rough sense, we know what the sensitivity of our detectors are. we have some, actually very poor, but some estimates of the rate at which black holes should be colliding. Okay? And based on those two things, we can make a prediction. And in fact, I did put up a prediction that in our next observing run, which will be about 6 months long, starting in fall 2016, based on what we've observed so far, we should expect to see something like 5 of these events.
Okay.
So, and the detectors are actually down right now for an improvement. So we'll run with improved detectors, and that should give us over a 6-month period something like 5 more.
Thank you.
Good. All the way in the back.
So why did you see Doppler shift of EM radiation when these gravitational waves distorted these vast distances?
So the question is, why didn't you see Doppler shifts of the electromagnetic waves when the gravitational waves distort the space-time distance? So the answer is that you do, but that's not the effect that we're measuring. So if you look out at the way that if you look out at the way that pulsar timing arrays work, they're doing that. They're looking at light from these pulsars. So these are neutron stars that are heavily beamed. And they're actually looking for shifts in the pulsar timing because of the gravitational waves intervening. So you can do that. Our detectors are insensitive to that effect, just at the frequencies we work. So, any other questions? So sure.
Yeah, suppose that I could hop in my TARDIS and get a little bit closer to the actual event. What sort of scale factor variation would I see if I were, say, in a solar system's radius of the event?
So the question was, if you could find a way to travel to this event and say where you got to close enough to it, maybe 1 solar system distance within it, what would the effects be on us? So it's a question that we've kind of asked, and one of the very first things, remarkably, that would happen. This is a calculation that was again done by my colleague Scott Hughes, whose sound I put up, whose sound encoding I put up. The very first thing is you might hear it. So it turns out actually that the space-time changes in your eardrum would actually register as you get closer in. So, what are the other effects? As you get closer to a black hole, the things we know is your clock will start ticking slower, but that actually won't be very measurable till you get quite a bit closer in. You certainly will start, your distances will, your meter sticks will also start to change. Those effects will also come a little bit closer in, but the very first thing you'll feel probably is the space-time distortion registering in your ear, remarkably. So that's what we think. Yeah?
And the time of collision can take because it's a very high frequency. But just before, is there any changes in wave shapes, or is it uniform?
Yeah, so the question is that does the wave change shape not just at the time of collision, but even before that? So yes, even before that, it's basically getting faster, and the amplitude is growing. Now, the rate at which the frequency is changing is quite slow when they're far apart, but it is doing that. And in fact, that was the way that Hulse and Taylor kind of can make their measurement. They are measuring a change in frequency of their timing pulse, of their pulsar. So let me just make a quick interruption. I think people need to go. I'll stick around for anybody who has more questions, but people who want to go should be allowed to. So come on down.